Now let's relate the standard value of delta G to the equilibrium constant. We'll do that by starting with our equation delta G equals delta G standard plus RT ln of Q. Now what we're going to do is invoke the restriction that we are at equilibrium. So if you're at equilibrium, then Q is equal to K and delta G is equal to 0. We can plug these two things into our delta G equation. So what we would say is that delta G is equal to 0. So 0 is equal to delta G standard plus RT ln of Q is the same thing as K, so I can just substitute in Kp. Now, maybe what I want to do is see how I can calculate the value of delta G standard if I know what the equilibrium constant is. I can solve for delta G standard by subtracting RT ln of K from both sides. And this would be how I could calculate the value of delta G standard if I know what the equilibrium constant is. Now, I could also rearrange this equation to see how you could calculate what the equilibrium constant is if you know what delta G standard is. So we could also solve this for Kp by dividing both sides by negative RT. So that gives us negative delta G standard over RT equals the ln of Kp. And then what we can do is get rid of the natural log by taking e to both sides of the equation. That will cancel out the natural log, because remember, e and natural log are inverse operations of one another. So when you do e to the natural log, those two things cancel out. We get is e to the negative delta G standard over RT is equal to e to the ln of Kp. And again, e and ln cancel out. So you're going to get that e to the minus delta G standard over RT is equal to Kp. So this equation allows you to find what the value of K is if you know the standard value of delta G and you know temperature. And this other equation up here that I'm boxing right now allows you to calculate what delta G standard is if you know the value of Kp. It's important to be familiar with both of these equations. And both of them allow you to relate delta G standard to Kp. Now we can go back to this reaction that we saw in a previous video where 2NO2 is at equilibrium with N2O4. We saw that the standard value of delta G for this reaction was negative 6.0 kilojoules. Now let's find the value of Kp for this reaction. To do that, we'll use the equation Kp is equal to e to the minus delta G standard over RT. Kp is equal to e to the minus delta G standard, so that's negative 6.0 kilojoules, over R. Again, we want to be dealing with energy units here, like in joules, right? So use 8.314. And to make the units compatible, I'm going to turn the joules into kilojoules right now. So 1 kilojoule is 1,000 joules. And let's say that temperature is 298 K. So this is at 298 K. Now, in terms of the units, let's talk through a couple things. So we have joules converted into kilojoules, and then kilojoules on the top cancels kilojoules on the bottom. Kelvin over Kelvin cancels out. And then you start to worry, like, oh, but I have a per mole here, right? So I'll again remind you that when you have a chemical reaction, it's implied that it's kilojoules per mole, right? So this is kilojoules per mole of reactions. And that per mole of reactions cancels out the per mole that you have from the units of R. This makes everything completely unitless, and equilibrium constants are supposed to be unitless, right? And the reason why is that you're dealing with exponentials. You can't have units in an exponential. You can't have units in the argument of a natural log. This is why equilibrium constants have to be unitless. When you plug this into your calculator, what you end up getting is that the value of Kp for this reaction comes out to 11.3. Now I'll remind you that earlier we saw an example. In this example, we had an initial pressure of NO2 of 0.01 atmosphere and an initial pressure of N2O4 of 200 atmosphere. And we calculated that the Qp under these initial conditions was 2 times 10 to the 6th. And so if you were to compare the values of K and Q for this, what we have is that K is 11.3 for the reaction and Q is 2 times 10 to the 6th. the value of K is less than Q, because 11.3 is much less than 2 times 10 to the 6th. And so this reaction would shift to the left. And that is completely consistent with the calculation that we did in our previous video, when we found that the delta G using these initial pressures was a positive value, right? The reaction was not spontaneous in the forward direction. It shifts to the left. And this also shows you another way that you can approach the problem if you know the value of K. You can compare K and Q and see, in this case, K is less than Q, and that gives you another explanation as to why the reaction shifts to the left. We could take a look at another example where we convert a value of delta G standard to a K value. So here we have the reaction N2 plus 2O2 is at equilibrium with 2NO2. We're told delta G standard is positive 104.1 kilojoules. So think about whether this reaction is spontaneous or not at standard conditions. Since the value of delta G standard is positive, this reaction is not going to be spontaneous at standard conditions. We could calculate the value of Kp at 25 degrees C using the exact same equation. Kp is equal to negative delta G standard over RT. And when you plug in the numbers here, you get that the value of Kp is 5.7 times 10 to the minus 19. And let's think about what that value represents. What does this mean? All right, so this value, 5.7 times 10 to the minus 19, is a very small value of K. And so that's indicating that this reaction very heavily favors the reactant side of the equation. At equilibrium, you would expect to have more reactants than you have products. So if you were to start the reaction with 1 atm of everything, the reaction should shift to the left so that you have more reactants than you have products. Right? So again, all of these concepts are consistent here. Now I'll tell you that any time that you have a chemical reaction where delta G standard is a positive number, when you plug a positive number into this equation, the negative sign out in front makes it so that you're raising e to a negative exponent. If you raise e to a negative exponent, you're going to get a value less than 1 and a reactant-favored reaction. If you have a situation where the delta G standard is a negative number, then the negative number for delta G standard cancels the negative sign out in front here, giving you a positive exponent for e, meaning that the value of Kp would be greater than 1. The reaction would favor products in that case. Let's take a look at one more example problem that relates thermodynamics and equilibrium. Here we have a reaction, Br2 plus Cl2 is at equilibrium with 2 BrCl. You're told that you start at standard conditions, 1 atm pressure for everything. You're told that at equilibrium, the partial pressure of Br2 is 0.86 atmospheres, and we need to find what the standard value of delta G for this reaction is at 298 K. Let's think about how we can use the information that we're given to help us find what we're looking for. There are a lot of ways that you can calculate a standard value of delta G. If you knew what delta H and delta S standard were, then you could calculate delta G using delta G equals delta H minus T delta S. But we don't know that, so we can't use that approach. You start searching through all of these different equations that you have, right? And one equation that seems kind of promising for us here is delta G standard equals minus RT ln of Kp. Because if I know what the equilibrium pressure of Br2 is, I might be able to use that to help me find what the Kp is for this reaction, right? Because the Kp for this reaction would be the equilibrium pressure of BrCl squared over the equilibrium pressure of Br2 and over the equilibrium pressure of Cl2. I already know the equilibrium pressure of Br2. So if I can find the other equilibrium pressures, then I can find the value of Kp, and I can find the value of delta G standard, and I'll have solved the problem. Now, in order to connect the initial and the equilibrium states to one another and to find all of the other equilibrium pressures, think about what tools you've learned that you already know you can use to find those things. Hopefully you remember that you can set up an ice table to do this stuff. So let's do that on the next slide. And again, this is one of those situations where when I do this example at an in-person class, that's when people start like groaning and they get really upset. And again, I'm kind of happy to be doing this in my home office where I don't have to hear that. So we'll go ahead and set up the ice table. All right, we were told that we have an initial of 1 atmosphere for everything. And now for the change line, let's take a look at the information the problem gives us. We're told that we start with a pressure of 1 atm for Br2, and we end with a pressure of 0.86 atm. And so that means that the pressure of Br2 is decreasing. So we'll do a minus X for the Br2, which means minus X for the Cl2 as well. It's going to be plus 2X for the BrCl. 1 minus X for the Br2, 1 minus X for the Cl2, and 1 plus 2x for the BRCl. Now, the problem told us also that at equilibrium, the pressure of Br2 was 0.86. And that helps us to find the value of x. So when you solve this for x, you get that x comes out to 0.14. Therefore, for the Cl2, you have 1 minus 0.14, so that's 0.86 as well. And for the BRCl, you have 1 plus 2 times 0.14, and so that comes out to 1.28. Now that we know all the equilibrium pressures, they can get plugged into Kp. Kp would be equal to our equilibrium pressure of the BRCl, which is 1.28 squared, over the Br2, which is 0.86, for the Cl2, which is also 0.86. The value of Kp for this reaction is 2.22, and now we're almost there. All that's left for us to do now is plug it into our delta G equation. All right, so delta G is negative R 8.314 joules per mole per Kelvin. T we're told was 298 Kelvin times the ln of Kp, 2.22. In terms of the units, what we have here is that Kelvin cancels Kelvin. Delta G standard for this reaction is negative 1,976 joules per mole. Or we could convert this to kilojoules per mole by dividing by 1,000. So that's negative 1.98 kilojoules per mole. And remember that the per mole of reactions is implied. You don't have to actually write it out. So you could also just say that it's negative 1.98 kilojoules. And there we have it. And this value of delta G standard makes sense and is consistent with what we observe in the problem, because this value of delta G standard tells you that the reaction is spontaneous in the forward direction if you start at standard conditions. In this problem, we started at standard conditions and we saw that the reaction proceeded to the right. You made more BRCl and you used up Br2 and Cl2. So that's all consistent here. Next, what we're going to do is talk about the effect of temperature on equilibrium, and we're going to get further insight into how changing temperature affects the value of K for a reaction.